You can make a full screen then, so.
How are things going as far as the course goes? Any comments? Any comments? We have an exam on May, no,
Not April.
April 4th. Midterm 2. April 4. Which is the Thursday. And homework 7. This is not ready yet. Shows up as under construction. I hardly started making it, so I want to put some new questions in there. And we have 8 weeks remaining. This is exactly the halfway mark between in the semester, in a sense. 8 weeks is finished. This is the 9th week. So I still should be able to cover sufficiently. Like we will do Poisson bracket, Kepler problem, and whatever time remains, we will do a bit of relativity in it. So that's our plan. We'll see how it goes. Okay, so today I want to do what is broadly called small angle approximation. And associated with that is called normal modes. Maybe normal modes should come first. And it is once we have our equations of motion, most of the times they are nonlinear equations of motions. That means the function is quadratic, not linear as a construction in the solution. But if we make small angle approximations, typically they become linear differential equations, and that becomes more tangible than other equations. So the best example is the simple pendulum that we have done. I'll again try to do a simple pendulum here. It acts like one of the simplest Lagrangian problem. We can get to the equations of motions any way you want to, either Newton's laws of motion or Lagrangian mechanics. We will do Lagrangian mechanics here. And from the point when we get equations of motion, how we proceed to get the modes associated with it is what we want to concentrate here. So let's quickly get the Lagrangian for the equations of motion, let's say. So we are talking about a pendulum, so okay. Example, we are talking about a simple planar pendulum, let's say. Planar pendulum. By planar, what I mean is that when I pull the pendulum, let it go, I'm not giving it any horizontal velocity. It is in the plane in which from the equilibrium line, if you want. So that's your equilibrium line. And we pull it apart, and suppose we let it go, and the equations can be written in terms of the angle of phi. Let's say this is L, and that's your mass M. And we have seen that our Lagrangian can be written in terms of the variable phi and phi dot. Dot means the time derivative, and it turns out there is no time derivative, explicit time dependence in the Lagrangian, so that's equal to half kinetic energy. It is moving on a circle of radius L, so it turns out to be mL square times phi dot square. So it's the idea that velocity in circular motion is the radius times the angular speed. It doesn't mean that the angular speed is constant at all. Could be changed. So that's your kinetic energy. Potential energy is minus of usually it is mg z, and here there is a, like, since it is in the reverse direction, so it comes out to be minus mg times cosine phi. You could say that this is the height h, but I think we talked about it last time. And either way you do it, so that's your potential energy, which makes it plus. So the potential energy itself is negative, so the Lagrangian is a positive quantity. Once you have the Lagrangian question, mgl cosine phi, very good, thank you very much. Otherwise even dimensions will not. Thank you very much. Good. So let me write this down more explicitly. So this is m L squared phi m g L cosine phi. Okay. Once you have the Lagrangian, the first thing, immediate thing you can do is find the canonical momentum. So that's your P. That's dl by d phi. So that's equal to ml squared. Do the derivative with respect to the coordinate, generalized coordinate itself, that typically is the force. This is the momentum. That's your generalized force. And in this case, this is equal to minus mgl sine phi. And once you have the momentum, generalized momentum if you want, or a canonical momentum, and the generalized force, they are related by your usual Newton's law. The total time derivative of the momentum is the force, right? Total time derivative of the generalized momentum is the generalized force. And in this case, this is d by dt of P is equal to dl by d phi, which is your Euler-Lagrange equation. And in this case, we get m, since time derivative does not act on L or M, so we have m L square by double dot, so that's a second derivative in time, that's equal to minus mg L sine phi. It's good to do some cancellation, so m can be cancelled out, one of the L also cancels out, and what's remaining is G over L. It's good to define G over L as a constant, and this will be the angular, the natural frequency of the pendulum. Like most of the time, everything that oscillates has a frequency of its own, and this will be the natural frequency. The word used is natural frequency, something that is inherent, that's a property of the system itself. So this is, let's call it omega 1 square. So very soon we are going to talk about two frequencies. So then we can do omega 1 and omega 2. So this is, so when I say normal mode, so that's there's only one normal mode in this scenario. So we can write our equation as phi dot is equal to minus omega 1 square times sine of phi. Right, that's your equation of motion. From this point, we want to do what is called small angle approximation, and I'm going to solve these equations in a particular way, which will be useful when we have more number of modes. Then it is a single mode. What's the solution for this? Actually, maybe I should wait for one more minute because by the way, what are the solutions for this? Any? No? Why not? Manuka says the solution is sine omega t plus cosine omega t.
This one is second derivative.
So, or my question is the solution for this A sine omega 1 t plus B cosine, right? Is that correct?
That one is with the phi t, this one is a derivative of phi t.
So that again, what I didn't understand.
Like this one is a regular phi t is equal to a sine omega t plus b cos omega t. But this one is second derivative.
Yeah, but that's an equation, right? Differential equation comes in terms of the second.
Yeah, that's why we have to.
No, that's not the reason. Is this?
The arguments in the signs are different. One's with respect to angles and the other is with respect to time.
This is second order time, right? That's one. So this is second derivative. And this is sine t. That's a t. And that's a differential equation that we derive. And typically we say that's your solution for the pendulum, right? I'm saying that's not correct. What's wrong?
You can also include initial conditions.
Okay, initial good condition, good, but those are there in the A and B, right? Plus initial conditions, plus initial conditions. Good, but something is, or put it like this, if I put this solution in here, will it satisfy the equation? Let's check that. Right, if I put this in here, it should satisfy it, right? You.
If there's a sign,
Exactly,
that
that's
term
it.
is gonna be,
Huh?
since there's a sign term, so we have to substitute that for another sign.
Yeah,
So it's gonna be an angle.
yeah.
Plus
So that again?
sign. Because of sign, I think we can't use that. I don't know much.
Yeah, we cannot, right? So, but then we always say that. This is the solution. To the pendulum problem, what's going wrong?
More angular concept.
Yeah, exactly,
You're in a
like
point.
this is the pendulum equation. This is not I should say not solvable in terms of elementary functions. This is not solvable, this is a sufficiently hard equation to solve. Like in these solutions are given in terms of elliptic integrals. So not easy to solve. But if you make the idea that, oh, these are small angles, so the pendulum doesn't stretch too far. How far? It depends on how accurate you want it to be. So if you're fine with 10% accuracy, you can go all the way to 30 degrees and you're good. So it depends on how accurate you want the problem to be. And 30 degrees may not make sense. Oh, how do you come up with this 30 degrees? Remember, pi is 180 degrees. So all this angle phi is measured in radians. And if you're in radian, 1 radian is how many angles? Pi radians is 180 degrees. So 1 radian will be how much? Approximately
By five.
180 by 5. What?
Five.
180 by 5. That's approximately 180 by 3. So that's 60 degrees. More accurately, it is 57 degrees. So 1 radian is approximately 57 degrees. So if you want accuracy, you want to compare with 60 degrees. So usually if you want 10% accuracy, or let's say 1% accuracy, then if you're within 6 degrees, that's good enough. Right? So that is how you come up with this 30 degrees, 60 degrees, and so on. But anyway, that's the idea is that this equation is not easy to solve. So we have to do what is called small angle approximation. So the next step, so this is the equation. Let me write this again. So phi dot is minus omega 1 squared times sine of phi. Use small angle approximation. The small angle approximation says that you keep your phi very small. Let's say phi is small compared to 1, right? And this 1 means 1 radians. So, and again, it depends how accurate you want to make it. You can make it slightly less, 1/10 of it, 1/100th of it, 1,000th of it, how accurate you want it to be. And in that case, sine of phi can be expanded. So that's phi minus phi cube over 3 factorial plus so on, right? If phi was 0.1, so example. So if phi was 0.1, then phi is 0.1 and phi cube over 3 factorial is 0.001 divided by 3 to the 6. Right? So that's really tiny. If I were to add this to that, that will change the 3rd or 4th significant digit. So you're pretty safe in making sine phi equal to 5 if phi was 0.1. 0.1. If it was 0.5, it may not be as accurate as this one, but still you might be able to get 10% accuracy. So that's the idea. And anywhere you get sine phi, you replace it with phi. That's a small angle approximation. And cosine of phi, you replace it with 1. Cosine of phi starts with 1 minus phi squared over 2 factorial and so on. So cosine of phi, you will replace it with 1. This is a very simple problem, so only phi shows up as sine in double pendulums. This will be more elaborate, there will be derivatives on the angle phi. Even there, you will do the same thing. So if you have sine of phi dot coming up, so you replace it with phi dot itself. Anywhere you get these kind of sine or cosines, even the derivatives, you just approximate it with sine and cosine to 1. Once you have that, your equation becomes phi double dot is equal to minus omega 1 square times phi. And that's an easy problem to solve. We know we know functions whose second derivative are the function itself, the negative of the function, sine and cosine are classic examples. So if I have this differential equation plus initial conditions, I know how to solve this. So the solution usually is phi of t is equal to a cosine omega 1t plus b sine omega 1t. That's what we wrote here. And a and b are determined from the initial conditions. That's how we proceed. But the simple statement that phi is a cosine omega t plus sine omega t, I'm going to do this using let's call it a formalism where we will arrive at the same problem, same solution, but it will have the advantage that even if there are two modes, for example, a double pendulum is not so straightforward an equation. There will be two solutions there, two equations, phi 1 and phi 2, two angles, right? Even there, we will be able to apply the new method that we are going to be learning. It's called, we will go to the Fourier transform of the, or the Fourier space, or the frequency space, if you want. Any questions at this stage? This is all a simple review.
So mode is determined by the angle.
Mode is this omega 1. Okay, so this oscillation, right? What is the oscillation frequency? That's omega 1, right? It's very, you could have identified it right here. So right at this stage, once you get this equation, you know that this will oscillate. Right. So the question is to give you a better picture of what we are addressing here. This is simple problem. But suppose I have a double pendulum. So this is M1, that's M2, that's L1, that's L2, that's phi 1, and let's say that's phi 2. Now there are two angles, and in the homework that either you're doing now or in the I think it's a previous homework, you derived equations for phi 1 and phi 2. And they're sufficiently complicated equations at the end. Is again not solvable. But if you make small angle approximations, they become two linear equations. The question is, what are the normal modes of this? If you have you ever played with double pendulum, or have you seen videos of double pendulum? Like you might see that sometimes what happens is that one of them oscillates with a frequency, the other one is just sitting there. And eventually one will stop and the other one will take over. So the main idea is that there are two natural frequencies. There is a natural frequency omega 1, which is G over L1. There is a frequency G over L2. But what is the actual frequency of the system? There will be two frequencies, but what is it? Is it the omega 1 and omega 2 that you get geometrically? Or are they constructions out of it? So what is the normal mode? That's the question we ask. Is that clear? And another thing you can see is, this is also how a laser works, is that in a park, if you have two swings, and if you are swinging on one, and let us say you're making small angle oscillations, you will notice that there will be a state if they're coupled, usually they are coupled from the top, right? You will stop moving and the other one will take over the frequency. Have you seen this system? Maybe I should show you guys. It is worth seeing this, okay. Let's see if this is. No. Make it simpler, maybe this.
Scarlet and Violet temporal forces play early at pre-release.
I've got two pre-megs making two pendula. I should. I don't know. This is about coupled pendulum.
I just randomly
This is a bit
picked,
of
so.
string, and from the bit of string, I've dangled two pendulum going through a pre-meg with a little button on the bottom to make sure that it doesn't slip off. Now then, if I bang one of these pendulum forward like this, it will eventually stop again. Look, I bang it like that, and at a later time it's stationary. And at a later time, it is stationary. It's magic. And I remember a magician showing this on a television show where he put a handkerchief in front and say, now it's stationary. And it would be. And then he'd open this one up and say, now this is stationary. And it would be. This is magic. Only it's simple laws of physics at work. We call these coupled oscillators. The reason is this is one
Yeah,
oscillator
that's-
and that's
So,
another one. They're coupled in a
just-
funny way with the string at the top.
Whatever
And
their,
there are little
natural
pulses
frequencies
as
are-
this goes out of line.
or one
Pulled from one to
approaches the
the
natural
other,
frequency of the
transferring
other.
into from this one, which
Okay.
is now coming.
Or that's what we will do. So now what will happen is that this
From
phi,
that one, I know.
cosine omega one, sine omega one, that will be cosine omega two, sine omega two.
I remember.
But what is the omega one and omega two? That's what we want to talk about. It won't be the simple L1, G over L1 and G over L2. If that makes sense. Or let's proceed. So keep this in mind, and it seems like that's a very, why would you be interested in this? This is pretty serious affair. Like if you're making a bridge, for example, there are the multiple natural frequencies, many natural frequencies. Let's take the simplest one, that if there is a bridge, it can oscillate this way, right? And it can oscillate this way also, like up and down also, up and down and this way. Take a ship, a boat, like if you're building a boat, it has a natural frequency to do this, and it also has a natural frequency to do this. So there is a coupled oscillator inbuilt in most of the systems. Now it is, if you're not careful, if the engineers are not careful, they don't make sure that they are separate apart, they will start resonating. One can fuel the other exactly like this. So you're trying to control this, but your ship will try to start doing this way. And that's not probably what you want. Like if you don't take care of it, it will do that and you won't be prepared for that. So it's pretty serious affair. Like you need to do this in every system that you can think of. Tell that again? Yeah, skyscrapers.
They also.
Exactly.
Dampers inside skyscrapers.
Exactly. Yeah, you can think of anywhere, every system you talk about. And what we would like to do is, like, I don't think I'll go into details, like when you think of a laser, right? So there are two modes. There is a photon there, and there is an atom. There are two, and how you can control one and get the other. So that's where we will try to motivate it a little bit. But this is everywhere. So, and most of the time, it is intrinsic. That's what I'm trying to tell. Like we cannot avoid it. That's what I'm trying to say, because same system will have more than one mode, and they can resonate between them, or at least fuel each other. So one of them can be the source for the other. So it's pretty dangerous in that sense. You're trying to go forward, but you get pushed in the sideways. Yeah, okay, that's what broadly we want to address. So buildup is one mode, but now if that is, I want to do the same problem again using a sufficiently sophisticated formalism, and which will be very useful for multiple modes when there are more than one modes. So Fourier transform. So we have phi as a oh, camera, yes, thank you,
Please untouchable.
please.
Jump.
Oh, and the
Please.
full screen, correct? Yeah, helps. That's really smart. Who writes that song? Right. Okay. So Fourier transform is phi as a function of time. Any function, the main idea is that any function of time can be expanded as sine and cosines. It is pretty much the idea of music. If you have a music, what you basically do is you press on keys, particular frequencies, and you can in principle get any sound you want to. But what you're pressing on is very specific frequencies. If you want, those are the sine and cosines. So what I'm going to write, sine and cosine can be written in terms of exponentials. We will work with exponentials. Yes, right.
No, just kind of adding, yeah. Like pressing different keys on piano is pretty much playing superposition
Yes.
and construction and destructive interference.
Correct. So maybe what I can say is that you would like to, so let's say that is A0, that means zero frequency, plus A1 sine omega 1t, let's say. So that's one frequency plus A2 sine of omega 2t. Maybe I should so omega 1 and omega 2 are related. So omega 2 t plus 1. And you can also get, let's say we want to put this in cosine also, right? This is b1 sine omega 1t plus. So now when you press your keys on the on a piano, you're actually controlling A1, A2s. This is a particular frequency, like frequency 440 hertz, right? If you give it a lot of amplitude, you decide this. If you press three keys, let's say this three together, you're having this, and this together. So you get a signal which is built out of A0, A1, and A2. You could have this to be 1, this could be 0.1, and this could be 5. Right? So you're getting a lot of this, less of this, and so on. And this is the whole frequency. If you put in all the frequency, the claim is that what Fourier showed us is that any function you can think of, absolutely any function, and I think the only restriction is that it should go to 0 at infinity. As far as that is satisfied, any function can be built out of this. So that also means that every function has a unique A0, A1, and A2. If every function can be built out of it, that means there is a unique representation out of A0, A1, and A2. So that's a very simple sketch of a Fourier transform. We won't work with sine and cosines, we will work with exponentials, right? They are equivalent, and any sum can be written as an integral, right? So instead of writing it as a sum over the frequencies, you say it is an integral over all the frequencies. So this is the same idea. Now all frequencies are taken care of. So I'm integrating over frequency. That's just a normalization, 2 pi. And instead of sine and cosine, I go exponential. And the minus here is just a convention. Usually if it was in spatial Fourier transform, this would be plus. In time it is minus, it's not necessary, it's a choice. So that in the, it respects Lorentz symmetry right from the start. Even if you don't do it, you can always make substitutions and get that, at another stage, you should be able to get that. This is, instead of A0, A1 and A2, we will call that phi of omega. So phi of omega is related to A1, A0, A1, and so on, and B1 also, right? So instead of A0, A1, I'm having this phi. So if I want to press the keys, I'm basically choosing my phi's. This is the amplitude of this particular key on the piano, if you want, or this is called a Fourier mode. This is the amplitude of the Fourier mode. So that's a picture. Now notice it seems like these two are identical functions. These are not. This should be a separate function. But often I will tend to use the same function on both sides, and the dependence should tell you that this is a frequency space and this is a time space. So every signal, if you want, or every function of time has a unique Fourier transform. So this is called the Fourier transform of phi t. It's good to know that one of the simplest function is a Gaussian, right? This is how a Gaussian looks like. That's your time, and exponential of minus, let's say, t square over tau square. And that has this nice feature that the Fourier transform of a Gaussian function is the Gaussian function itself. So it will be, so Fourier transform of this would be exponential of minus omega square over, there will be a new function, let's say omega tilde square. The shape of this function will be identical, and this you use it, exploit this in quantum mechanics a lot. If you have a wave function of this kind, its Fourier transform will be again exactly having the same shape. It might squeeze or it might stretch, so that is all possible. So that's your Fourier transform. Any questions or comments at this stage? Okay. Okay. So if there is a unique Fourier transform for every function, instead of solving for this, I can try to solve for this. Once I have this, I just have to do this integral to get the solution. And there is this great advantage in the Fourier space, that in Fourier space, most of the differential equations becomes algebraic. We don't have to solve differential equations, we can do algebra in the Fourier space, and then we have to do this integral. So the price you pay is that eventually you have to do an integral. But differential equations are easy in Fourier spaces. They become algebraic. You basically solve simple equation. So let's see what do I mean by that. So let me substitute that in here, right? So in this differential equation, so I have second derivative of phi is equal to minus omega 1 square times phi. So substitute that. T square, this is phi of t, right? So that's equal to minus infinity plus infinity
Yeah, minus omega 1 square plus y plus goes twice, we get minus 2. No,
Again?
second derivative of exponential 2 times.
Oh, I didn't do that yet. Yeah, I haven't. No, this is omega 1 node.
Oh, okay.
You're thinking ahead of me. You're ahead of me. That's the next step. You're ahead. Okay, good. So I think what Manuka is pointing out is that on the left-hand side, I can take the time derivative inside of the integral. This is a frequency integral. So this can go in to the integral. And the only place where it hits the time is here. That's only exponential. That this is all frequency dependent. Right? This is all time dependence is only in the exponential. I know how to take the exponential derivative. It brings down the argument of the exponential. So every derivative I take, I bring down a minus I omega down. So this is equal to minus infinity to plus infinity, the omega over 2 pi times two derivatives is minus I omega square times exponential I omega t by tilde omega. And if you want, this is equal to plus omega 1 square observe minus I square is so this can be written as minus infinity to plus infinity. This is minus, so this is omega 1 square minus omega square. I changed the order. First wrote omega 1, then wrote minus omega square by tilde omega is equal to 0. Is that clear? If you go back to this function, if I tell you that each of these coefficients, A0, A1, A2, B0, B1, everything is 0, what can you say about the function itself? Like, expectation is that it will be 0, right? Even though when there are infinite zeros, one should be careful. Maybe it can add up to something finite, but naively speaking, all are zeros, phi should be equal to 0. This is a Fourier transform, this is 0. Right? This is the Fourier transform of this quantity. So that's your Fourier transform. Phi of t now is 0. So this, the Fourier transform of this quantity is 0. Is that clear? Okay. And you can also think of it as a vector space. So these are Fourier modes. These are the coefficients associated with that. If there is a vector that is 0, then each component is 0. So this is an infinite dimensional vector space. Each component of the Fourier mode is 0. Okay. So starting from this equation, what I've learned is that if this is true, this must be 0. So phi double dot is equal to minus omega 1 square times phi of t, let's say. That's t. This in the Fourier space becomes minus omega square phi tilde omega is equal to minus omega 1 square times phi tilde omega. And this can be written as omega 1 square minus omega square. I wrote an in between step because this is what you get if I were to replace this time derivative with minus I omega, I immediately get this. So I'm doing two swaps and phi of t to phi tilde of omega. So if you have only simple derivatives in the differential equation, it's very poor man's Fourier transform is replace all the time derivatives with minus I omega. Replace the phi with phi tilde, and you're done with the Fourier transform. Okay. It's sometimes it doesn't work, or I should say often it doesn't work, but in most of our problems, because there will be only time derivatives sitting there, it will be very easy and it will work out all the time. Is that clear? Right? So just and you can see how it is happening. This enters and it always will pull the time derivatives. So it always, most of the time, goes through. Okay. And that's not a differential equation. I told you that it will be an algebraic equation, right? This is algebra. Like there is no differentiation showing up anywhere. So if I can solve this equation here, and then I do the integral, I'm done, right? And the claim is that I'll get this solution. So now let's look at this carefully. This is an algebraic equation. What's the solution of this? If I tell you that this is true, that is a function of omega, what can you say about phi tilde here, if that equation is true?
Until there will be equal to 0.
Yeah, phi tilde should be 0. If that's equal to 0, phi tilde should be equal to 0. Right? That's surely good observation. But if that is 0, that's 0. And I don't get any solution, right? But that is a correct interpretation. But there's something more to it. Is it always 0?
Only
Omega is not equal to omega 1.
Exactly. If I have product of two quantities equal to 0, either this could be 0 or that could be 0. What you guys have said is that if omega square is not equal to omega 1 square, then it has to be 0. Then there is no other possibility. But there is this possibility that omega square is equal to omega 1 square. And then I can put in anything I want there. It could even be 0 if I want. If this is satisfied, I get my 0. As far as it's not infinity, anything that is not infinity is a possibility there, right? It could be anything. So let me say that's alpha times omega. Sorry, alpha as a function of omega. Good point. Like it's any arbitrary function, and what is alpha? I don't know. This was not known to begin with, phi tilde. So I don't know alpha either. It's some unknown, but it's not phi itself. It is some function, and apparently only works. It is non-zero only when it is equal to omega 1. So that's the feature in them. That's very similar to something we are used to, delta function. Right. So apparently we should be writing this as a delta function. So maybe like write this as alpha omega times delta of omega square minus omega 1 square. Right? If this is equal to 0, delta function property makes sure that it is 0. If it is not 0, then there is this feature that delta function can be infinity, and so typically you don't work with delta functions just because you want to avoid infinities, but I think we are very comfortable in using it. We know a lot of properties of it, so we will use delta functions. So the solution is it is non-zero only when omega square is equal to omega 1 square. That's the mode if you want. You have selected the mode right here. In this case, it was a simple case. There was only one mode. When you're doing multiple modes, this equation, this is where the complication will be, there will be two modes here. This will be not a quadratic equation, it will be a quartic equation, fourth power equation. So there will be four modes and two of them will be identical. So that's how they will work. And from this to this, it will be very similar, except now there will be multiple delta functions. We'll see as we proceed. Okay, any questions at this stage? Okay, so we are used to delta functions of x, y, right? This is a squared quantity. How do you do this? What's the delta function of x squared? So what I mean is, if you have integral dx f of x times delta of x minus a, that's equal to how much? F of a, right? Very good, right? But what if it is x squared? What is that equal to? Oh, we solve for x, very good, right? So moment you have something here, then you solve for x, right? Very good. So x squared minus a squared is equal to 0, right? And you would say x is equal to plus or minus a, very good, right? So there are two solutions, so that can be f of a, right, when x is equal to a, or f of minus a, there are two solutions, right? And it is some here, but what's the coefficient here? That's correct, it is, the first important point is that there are two solutions. So we get that f of a and f of b, but there are coefficients in front. How do you decide on that? See this in electromagnetism also. So here is how, this is the general formula. X f of x delta of, the quadratic was a simple case. In general, this could be anything, right? This could be a function in itself. Right, let's make it really elaborate. First, we set g of x equal to 0. Correct, we do this, and that's a hard part, to find the roots. Right, roots are not always easy. Quadratic equation, it's easy. For even quartic is easy, but after it is pentic, it's not solvable most of the time. But let's say you know the roots, right? So x1, x2, x3, and so on. So let's call it x of r. Okay, so these are the roots of this equation. XR are the roots of, so that means g of XR is equal to 0. Okay, so that's your root, so that's your plus or minus a here. So you have to add, so the answer is you have to add up on all XRs, the sum over all XRs. And of course, there is f of XR. Right. Evaluate this at x of x. So that's what I wrote there. But I'm interested in the coefficients. The coefficients are determined by this. It is you evaluate the derivative of g. The function that was there inside, take the derivative of that. This can be proved relatively easily. Somewhere else I do that, I think. In electromagnetism, when you do radiation problems, you do that. And then you evaluate this at x equal to xr at the root. And you have to take the magnitude of this. So few steps. So it's easy to forget to take the magnitude. It's easy to forget to evaluate it at x of r. So that's what it is. Okay. In our case, it is straightforward. You take the derivative, right? Take the derivative of this, that's 2 times x. A derivative with respect to x is 2 times x. Same thing here, 2 times x. Evaluate x equal to a. Evaluate x equal to minus a. And then you take the magnitude. Right, so this is f of a over 2 times a magnitude plus f of minus a minus 2a, you take the magnitude, which becomes plus 2a. So it is the sum of f of a and f of minus a and divided by 2a. Okay, clear? Okay, with me? Okay. Okay, so our solution then, f tilde omega is equal to, in our case, so it is alpha omega. This is the same as delta. So you can say this is delta of omega minus omega 1 divided by, basically you're providing this all the way here itself. So that's 2 omega 1 plus delta of omega plus omega 1. This is not exactly this, but if I use this, I will get this. That's right. Or you can say, you can remove the integral and say that this is equal to delta function over this. With me? We are interested in 5t. 5t is integral omega over 2 pi exponential minus I omega t times phi tilde of omega. But what we have said is that the Fourier transform of this function has only 2 modes, plus or minus. Either it can work with plus or minus. There are only, so basically you say single mode because plus or minus frequency doesn't matter. But it is 2 modes in the sense it is cosine and sine. Those are the terms, exponential plus and exponential minus. Substitute this in. Omega 2 pi minus I omega t, and this is can be pulled out, I suppose. Alpha omega over 2 omega 1 delta omega minus omega 1 plus there are 2 integrals in this. Each one is easy. Whenever there is a delta function, I just have to replace omega with omega 1 everywhere inside the integral. Right? When I'm doing the first case, this gets replaced with omega 1, this gets replaced with omega 1. So I have exponential minus I omega 1t. Then I have alpha of omega 1 over 4 pi omega 1. And in the second case, I get plus exponential of, so when it is minus, it becomes plus, right? Plus I omega 1t alpha minus omega 1 over 4 pi omega 1. Remember, alphas were completely arbitrary, right? But these are no more functions. These are numbers, right? These are evaluated at omega 1. Here we said it was a whole function there. But now it's evaluated at omega 1. This is a number. Call that A and call this B. Right? So that's here A times minus I omega 1t plus B times plus I omega 1t, and that's your solution for your pendulum, where A and B are initial conditions. If you want alpha of omega 1 and alpha of minus omega 1 are initial conditions, are determined from initial conditions. But we went through a long, elaborate process to get something very straightforward. But this process will work for multiple modes, for a double pendulum and so on. It will be very straightforward. And it was not that complicated. There was differential equation became an algebraic equation. This becomes important. We have to solve for this. It will be a matrix. When we do this for a double pendulum, this will be a matrix equation, and it will be the determinant of that matrix that will come in. We will talk about that. And from that point on, everything stays the same. And after a few times, after you do a couple of examples, you realize that I don't have to do much. First, I solve for the modes here, and I just substitute exponentials for each of that mode. Cosine, sine, cosine, sine, and initial conditions decide your A and B. So the important steps are just solving for the modes and then finding the initial conditions. So your homework problem, you will fill in these steps, but this is again single mode, so we will do this for multiple, at least 2 modes, not 3 modes. So it gets hard pretty quickly, or tedious very quickly, not hard. Okay. Any questions at this stage? So this is mainly what I want to say, but I'll do some more maybe since I have time. Go ahead.
So the second step,
Mhm.
so did we write that using like, since the both integrals are the same on the both sides, we can use only those two terms, they both step.
This one.
Yeah.
Correct, correct. Because omega is inside the integral, so what I am doing is minus infinity to plus infinity, the omega over 2 pi minus omega t, omega square, there's a minus, I suppose, right? And pi tilde, that's equal to omega 1 outside, the omega over 2 pi e raised to minus I omega t pi tilde. Right. These are like 2 vectors. Think of it as vectors. These are your unit vectors. Like you call it basis functions in this case, right? If 2 vectors are same, its components are the same. So these are 2 vectors, components are this and this, right, with the omega 1 square. So they must be identically matched. That's another way of, so you can say, oh, why is that allowed? The simple statement is that Fourier space is a complete, or Fourier functions are complete set of functions. If you can expand any function in terms of these functions, then they have a unique representation associated with them. So if there are 2 representations, they must be identical. Like it's exactly like vectors, that this finite, this is infinite. Okay. Just to give you a feel for how this becomes multiple, and since we have about 10 minutes, let me do that. We'll do that again, a more concrete example next time. So let's say you have some system which has 2 modes, and there are 2 angles, like double pendulum is a possibility. Phi 1 double dot, that's 1 angle, that's equal to minus omega 1 square times phi 1, right? That's your one of the pendulums. The second pendulum is phi 2 double dot minus omega 2 square times phi 2. These are 2 decoupled pendulums. Like think of a bridge that is oscillating in the vertical direction and in the horizontal direction. These are its 2 modes. And these are decoupled. Phi 1 on the left connects with phi 1 on the, or phi 1 on the right connects with phi 1 on the left, phi 2 on the right connects with phi 2 on the, completely decoupled. But I can couple them. I say that, let's say this is plus some coupling constant, let me call that alpha, let's say, times phi 2. That means whatever is happening in the second mode is acting as a source for the first one. Right, remember forced oscillators, forced harmonic oscillator? This has become a forced harmonic oscillator now. Right, so let me rewrite this if you want. So it's forced harmonic oscillator just to show this better. Plus omega 1 square phi 1 t is equal to alpha some constant times phi 2 t. Forced harmonic oscillator is whatever is there on the right, is called the forcing function. Right? Do the same thing here, maybe just to make it maybe alpha times by 1. By 2. That's equal to minus alpha times phi 2. It doesn't have to be minus, I just arbitrarily picked. So let's say beta, right? Since I'm not going to be solving this problem here, I can say alpha and beta. Okay. The coupling need not be the same, but we will see that in most of the coupled problems, these alpha and beta will be identical. They will be related in a sense. Notice physically what is happening. Whatever is going to happen, even though this was not moving to begin with, this was completely isolated. You have a bridge that is oscillating in the up and down situation. That's your phi 2. But phi 2 becomes a source for phi 1. And it starts oscillating horizontally. And remarkably, what we will see is that even a tiny bit, even an extremely tiny bit can do the job. It is not necessary that it has to be significant. We will see that even in the 5th decimal, like we are working in 2 significant digits, but this alpha could be in the 5th, or for that matter, 10 raised to minus 34. What is 10 raised to minus 34 significance? The 34th significant digit? That's a Planck's constant. So even at the 34th significant digit, something could happen and it could affect it. And that's quantum mechanics in a sense. If you want to connect with quantum mechanics, you have something happening at a scale which is entirely far away. You wouldn't expect it. But if all the conditions are right, you can get an effect like this. And we will show that next class. We will see that even if alpha is really tiny, if I choose it will be basically omega 1 and omega 2 are equally tiny. I can get this effect amplified significantly. So my point is that alpha could be small, really small, 34th quantum effect, like by quantum I mean in the 34th significant digit. And omega 1 square minus omega 2 square is also 0 as you want. But these two are of the same order. The coefficient, the fraction of this, like for example, 0.00005 divided by 0.000001 is equal to 5, right? So this could be small, but if these two frequencies are equally small of the same order, then I can get a very big effect if I want to. And that's what we will see, and that's why that's important. So the idea is not to keep this small. The idea is to keep this away from these two. That's a very fine limit in a sense. So we'll see that how that shows up. It's kind of neat. Okay, that's all. Still, this semester I'm doing very good.